Hey guys, got another Kels update for you, and we're really excited about this one. We've quietly been working on a DRS rear wing system for Kels since we found out that our engine, we weren't going to get the big bore upgrade that we were hoping for this year. So we needed to find another way to get some more straight line speed. And so we just went for it. And we're going to do a whole breakdown of this video for you. You're going to see exactly how it was designed, the CFD, the mechanical, the pneumatic system, the whole thing. So yeah, we even made a model in Assetto Corsa, and we'll give that to you guys. So if you watch the video, you get the download link, and you can drive the real-life Kels with working DRS in Assetto Corsa. All right, guys, so this is the wing that we came up with. You can see it's kind of complicated. It's got this beautiful cantilevered swan neck design. Obviously inspired by the Ford GTD. I love the design and the look of it. That wasn't the only reason though. We wanted to pick up force off of the chassis, which, like, there's just nothing behind here, really. So we've had a DRS design in years and years. I've been changing it and doing different things. So we'll talk about all those different iterations and why we settled on this design. But we basically wanted to do a pneumatic system, so air-powered, because we already have paddle shift. And safety was really first and foremost. I mean, if you have a DRS failure, if the flap fails open, you go from having, say, 40% front downforce to 70, and the car will just spin like a top. Like you saw at Suzuka, if you watch F1, Jack Doohan tried to send it in with the DRS open, and the car just went in the wall. So we were actually surprised to find out that in F1 you have to press the button to turn off DRS. In the software that we wrote for this car, there's a bunch of fail-safes that wouldn't allow that to even happen. So that was kind of surprising and shocking, actually. So in a sense, this car is more advanced than an F1 car in that respect. And we'll also talk to you about how the simulation in Assetto Corsa was so useful in predicting. We figured this will be about 0.6 of a second of lap time improvement at a track like Road Atlanta. But at a smaller track like Lime Rock, you come out of the last corner already going very quickly, and it's a short straightaway. So we're only going to see probably about 0.1 of a second improvement at Lime Rock. So it's a huge amount of work, DRS, and it's really only useful on like big boy power tracks, but we needed something if we want to keep up with these 1,200, 1,400 horsepower, twin turbo, American muscle cars. So at least the DRS helps us get that speed at the end of the straightaway that we just can't get with a naturally aspirated engine, even with hybrid assist. Okay, so the mechanical bits of the wing. Like I said, we wanted to copy or take inspiration from this beautiful design that Ford did with the GTD. And it made a lot of sense on the Z too, because we just have no structure behind these strut towers. And as you know, if you're a Z fan, there's this big strut tower structure from factory. So there's a lot of meat there for us to grab off of. So the first thing we did was whip up a steel bracket that we could weld to the chassis with 3 holes. And then we had to come up with this really crazy design. We didn't have to, but I really didn't want to have this beautiful wing with bolts and connectors and air lines all sticking out of the trunk. So I wanted to have a really slender, like 11 millimeter wide upright that just came out of the trunk. And you didn't really see all the other electrical and pneumatics systems that were connected to it. And I also wanted to make the wing really easy to remove for no reason. Like, there was no need for this. We never go in the trunk. It was kind of pointless, but it was just kind of like a fun thing we try and do. So to keep everything within 11 millimeters wide and have it to be quick disconnect, that means that this whole wing assembly here, it just sits in there and it's like interlocked in this receiving bracket. And the lines to fit in, we had to use O-rings for it to be able to go quickly in and out. And obviously, as this assembly is kind of slotting in, those lines need to have some flex and some give. So we made these brackets that are just a bit set back from the airlines. And then when we slip it in, all we need to do is plug these guys in, slip the wing in, and the air system is connected, and all the mechanical load can go right down through this really overly complicated bracket. That, to be fair, I put no effort into making easy to machine. I just didn't care, and we have the best machinist, and he just figured it out, which is I'm very thankful for, because, yeah, you need a 5-axis machine for most of this ridiculous stuff. I mean, we have everything super tight. Even the lines are almost touching each other. It's maybe pushed a little bit too much to kind of cramming everything in together. And then, so the last kind of thing in that interface that's left is how do we pick up the wires? So right now we're just using a connector, but we actually have a plan for some little electrical contacts. We're hoping that those will work with the vibration of Kels at high speed. And if not, we'll have to have a little connector, which would be too bad. So then from these uprights back, I designed them all and did some FEA on them to see that they could handle about 1,200 pounds per upright. And with these carbon inlays that'll bond on, that'll give a lot more structure and stiffness to the upright. So hopefully that doesn't snap off. We'll find out the first time we try and go 280 kilometers an hour. But the real goal was just to keep everything super slender. And as you can see, the actuator just sits on top here of the upright. Now, there was a previous design where I had all the linkages and actuator down inside the trunk area, but the concern with that is you just got all these opportunities for linkages to bind and become problems. So even though this is in the airstream, we'll have a nice cover over it, and it's just a straight shot to the flat. And then the real challenge for us was figuring out where to put this pivot point. And just aerodynamically, we wanted the system to always fail closed. So everything about the system is designed inside this actuator. There's a spring that's always pulling back on the flap. And once the flap closes a little bit, the air just sucks it shut. So it was really just, how can we make this system fail in a way that doesn't destroy the car when I enter the next corner? So hopefully we did it right. And now let's take a look at kind of the more aerodynamic design aspects of it and how we did figure out if it was going to fail open or closed. All right, so before we could do all this mechanical design, I needed to figure out one thing. I really wanted to get the flap to aerodynamically close. So if the flap is open, I wanted the air to suck it shut. I figured that if we put the pivot point at the right location, this should be possible. Turns out I was wrong. We put this setup, we made some steel end plates and suction cup mounts, and we threw them on our Model 3. And we used a really advanced system to open and close the flap that consisted of Jesse out the window with a broomstick. And we tried all kinds of different pivot points and angles, and we found that no matter where we put it, the air flowing kind of over the back of this flap was enough to counterbalance any downforce from the front of the element, which I thought would really suck itself down, but it doesn't. So at that point, we kind of realized that, okay, we need to put springs in our actuator. So even if the air system fails, we have like an overwhelming amount of force that's trying to close this flap down. So we're not relying on an electrical system or air pressure to pull the flap shut. We then ran the whole system through an AirShaper, which is the CFD tool that we use. It's a cloud-based service that's really convenient. You can kind of upload any file and it just figures it out for you. And I ran, I kind of put the wing where I wanted it, and I ran it with the flap open and closed, and we're able to see exactly what the force is on this flap element and how much torque is being applied to it. So from that, we can figure out exactly how much force at 300 kilometers an hour do we need to be able to open the flap, and how much force do we need to be able to suck the flap back closed. And the interesting thing is when we were testing with the Model 3, we found that it takes a very little bit of force to nudge the flap. Just once you get down past about 6 degrees, and then it just slams itself shut, and it just holds itself shut as you kind of expect. So the force to open it is really great. The force to close it is almost nothing. So we wanted to use a spring system that would, have a lot of force when it's open to get it to shut, but we didn't want to have so much spring force when it was closed that it was reducing how much power the actuator had. Because if we want to open the DRS at 220 or 230 kilometers an hour, we need quite a bit of force to break the air and get that flap opening. So we'll talk a bit more about that actuator now and kind of how we designed it and how we figured out how much force we would need and how we could design it to kind of get both of those things checked off. So we ran through all the CFD. We obviously want to see what are we gaining here, right? What's the reduction in drag? And the important thing is, what is the improvement in efficiency? So with the wing closed, how much downforce do we have? And with the flap open, how much drag do we have? And that kind of gives us the efficiency of how much downforce we have per unit of drag. And kind of a good benchmark that I was always targeting was an LMP1 hypercar. Those are these new prototype race cars that manufacturers are allowed to design kind of to whatever shape they want, but they can't exceed an efficiency of 4 units of downforce for 1 unit of drag. So with this setup, with the DRS, we have 3.5 to 1 aerodynamic efficiency. So that's pretty good. We were at 2.5 before. And to give you some perspective, I don't have the numbers in front of me, but at about 220 kilometers an hour, having the flap open is saving about 80 horsepower worth of drag. So it's like the engine's gaining 80 horsepower and then 100 and then 140. And the faster you go, the more effective horsepower you're getting, because you're taking that power that the air is slowing the car down and you're just freeing it up. So it is very substantial, but again, it only really adds up to a lot of lap time when you've got a long straightaway where you accelerate up to 230, 250 kilometers an hour, and then you stay there for a while. And then that difference of where Kels would arrow out and stay around 260, now we'll be able to do 290. You know, if you sustain that for some seconds, then you'll see the lap time improvement. And that's why it's the Road Atlantas and the Circuit of the Americas, those types of tracks where the DRS is going to make a difference. Okay, so we had to design our own actuator because there just wasn't one commercially available that would do this job. And so I've taken one apart here so you can kind of see the guts of it. But there's a stainless steel piston that has 2 seals on it. There's a spring, and there's this 3D printed spacer here, which is actually on the other side a magnet. And that's how we do the position sensing. So for this guy, we knew from the CFD how much force we needed to make. So we made the actuator big enough so that at our 8 bar of pressure, which is like 120 PSI for you Americans, we have enough force with one actuator to open this flap up to about 200 kilometers an hour. And we have 2. So we should have plenty of force. I believe we measured these to be 160 pounds. So we've got 320 pounds of force to open this flap. Otherwise, I mean, early on in the design, I wanted to rely only on the spring to close the flap. In hindsight, I was thinking, you know, if I'm going into the wall, I'm going to be really wishing that I had just put the air on the other side and we could have closed the flap and covered some binding or some stiction in the system that the spring couldn't overcome. So I redesigned the actuator, put a seal in here, and now there's a fail-safe system that if the spring isn't closing the flap fast enough, the actuator will fire to close the flap and assist the system. So we'll have 300 and something pounds plus the spring shoving the flap shut. So, I mean, there has to be some major problem for that flap to not close, especially when this thing's all in bearings. You can see how easy it is to open and shut. So that's kind of it. I mean, it worked first try. We were super excited about how this pneumatic design that I've never done before worked out. And we'll have to see on the racetrack if it gives us any issues. But so far, it's looking pretty good. The last step to this thing before we get into the electronics is that magnet. So using a Hall effect sensor and a custom PCB I designed, we can see the exact position of this piston. And using 2 sensors, we have some redundancy. So even if one sensor fails, we know that something's going wrong, and we know either this guy's closed or open. And with that, we can do a lot of safety to kind of warn me as a driver seconds before the braking zone of the corner that something's gone wrong, the flap might be open, and those couple of seconds is the difference between being able to brake in a straight line and keep the car somewhat stable versus not being able to make it and losing control. All right, well, we're on to the electronics of this whole DRS system, and I'm told we're running a little short on time, and since you guys have the attention span of flies, we're going to get through this a little bit quickly. So the real thing about DRS, like I've mentioned, it's just so dangerous if it fails open. And the advantage that we have here is that we have this Motec M1 software environment that we can really quickly write really advanced programs and strategies to kind of get around this. So a few ideas that I had was, number one, we'll use a lap distance trigger. So we can set 3, 4, 5 seconds before the braking zone to close the DRS. And in practice, what this means is that you just stop accelerating for those 4 or 5 seconds. It's not a big difference in speed, but now I've got 4 or 5 seconds to react if there's a problem. We also set up fail-safes that will close the DRS if there's too much wheel spin, if there's too much lateral G-force. So if I'm turning too much, the flap will try to close. It won't wait for, like in F1, for you to let off the gas pedal or press the brakes. Although those are also in there, throttle pedal, brake pedal, all the stuff you'd expect. And then we have to deal with, what do we do when the flap is not doing what we want it to do? So the first step is, okay, that took way too long to open or close. So that says maybe something in the system is binding, or maybe there's a problem and we have air leaking. So if the system takes too long to open or close, it'll fire the closed solenoid all the time, try and keep the flap shut, and totally disable the DRS until the ECU is reset. Because we don't want to just be able to clear that alarm. I know myself as a driver, I'm just going to clear it and try it again, hope it works, because that's what happens when you have your helmet on. This is set up so that if there's a failure, the DRS just faults out and it does not clear until you reset the ECU. So with all that said, the hope is that if the system doesn't work the way it should, I'll be notified early enough to be able to brake in a straight line and get the car down to a speed where the aero imbalance doesn't make the car super impossible to drive. And then we just kind of made a little quick display on the C187 here that just shows all those systems. So if it's showing green, we know that those conditions have been met. And it just shows the position and the status of the system. And it also shows an animation of the flap moving in real time. So yeah, the last thing that's kind of cool is the flap will always try and close itself if it sees that it's been open. All right, so we've got Jess here, and we're just kind of showing how the system works. Jess, do you want to try and open the flap? Good. It doesn't like that. It does not let you open it if it's not supposed to be open. Let's show you how it works when it is supposed to work. All right, so this is what the screen looks like. You can see that everything's armed except full throttle. So Jesse's hand is going to be the foot that's going to press full throttle now for Jess. So now the system's armed. You've got this green light here. And when I press the button, the flap's going to open and these lights are going to go blue. Just clear this ABS fault. We don't care about you. Here we go. And then when we let go of it, the lights go yellow to show that it's trying to close. And then green means it's still armed. And if Jesse lets off the throttle, it's not armed anymore. And if we're the wrong part of the racetrack, it wouldn't be green either. So that's kind of like the display the driver gets with the lights to be able to know what's happening and why. If these lights are all yellow, I know it's trying to close and can't. That's really bad. And there'll be another screen that comes on the dash that'll say, you're going to die soon, so do something about it. So that's kind of our DRS system, guys. There's a little bit of a nerdy deep dive for you. I hope you enjoyed it. If you did, share it to your friends. And your reward is that you can drive Kels in Assetto Corsa. So before we had the hybrid system modeled, and now we also have the DRS. And we used to have a lot of fun at the Nürburgring, Mosport.
Yeah, we need to set that up again.
Yeah.
It's just, it sounds like the real car. It drives like the real car. The lap times are correct. I haven't tried it with DRS though.
Yeah, now with DRS, it's even more fun.
It's animated, right?
It's animated. You can actually see the flap opening and closing. Yep. Super cool. So the download link is on our website, Mountain Pass Performance. You go to Project Cars and KERS Kels, you'll see the page there. And also, we probably put it somewhere here. This way, Adam? Or this way? This way? So yeah, maybe there's a thing there. Maybe there's not. You might have to do some work and actually enter an address in your browser. But it's worth the hard work because the car is super fun to drive in Assetto. And it's been a huge tool for us too, like learning new tracks, getting to know how the car is going to feel, doing the aero balance, seeing what the DRS will be like when it's open as a rough idea. These are all really valuable things. Track time is super expensive. And being able to practice and do this in the sim saves us a ton of money. And it means when I go to the track, I'm not trying to get up to 80%. I'm already at 90%. And I'm just finding the little differences. So yeah, really, really cool tool to not just have sim racing, but to make your exact car and use that as a base to learn the tracks is even more precise. So yeah, thanks for watching. Hopefully this thing works great on the racetrack, the way it works while we're not moving. And hopefully we have an engine soon so we can go rip this thing.